And we're back. Hello again. This is the last part of our exploration of thermal measurement methods, and probably the method that is most important. So I encourage you to go to the literature and out to the web to study on this intensively, because in all likelihood, especially for those of you who go off to work in industry at some point in your life and work with material systems of essentially any form, my guess is that you will encounter this type of measurement. And of course, I'm speaking about differential scanning calorimetry. So let's jump right in. So DSC, as the slide shows, stands for Differential Scanning Calorimetry, and very much like DTA type of measurement, except that the heat input to the sample, the reference, is varied in order to maintain both at a constant temperature. So whereas in the former case what we were measuring was delta T, what we're measuring in this case is that we're looking at like how the energy flow into the samples are different. And in point of fact, this is far easier to use, but actually the most important point is, despite all the things related to issues of servo control and everything, like how you actually make an instrument work, perhaps being more easily implemented, what's actually critical in this case is that DSC actually allows you to quantitatively measure things that actually have important characteristics. For example, for materials undergoing phase transformations, you can measure those thermodynamic attributes with high analytical accuracy, and can do so actually on relatively small sample sizes. So a differential scanning calorimeter looks a lot like the kinds of instruments that I showed you in earlier slides, and they have a little bit of difference, seemingly subtle, depending upon whether or not they're so-called heat flow DSC or power compensated DSC. Basically, they're just two different methods of doing the same measurement, and those differences are relatively minor. So I'm not going to go into it very much. In great detail, but like to note, right? We have a sample and reference phase, and basically the instruments would be designed to let us, maintain both the sample and reference, and to control the temperature in the background, such that the temperature in the sample and reference is maintained at constant temperature, one relative to the other, as a differential temperature ramp profile is being initiated, but to do so in a way that we can actually measure the change of the energy flux into each of the two components, right? So basically, this will allow you to say something about the fundamental quantitative attributes of the kinds of transformations that we saw evidenced in differential thermal analysis. Okay. So, like just to give you an illustration for what this might look like, a DSC actually will have to have a lot more channels of measurement associated with it, right? So, like for example, if we have to measure heat flux, that has to be implemented somehow. So, like in a heat flow DSC, that is actually measured by looking at how temperature gradients are manifested across a system of measurements that radiate out from the sample, and look at, while we maintain the temperature as a constant in the two samples, right? There may in fact be a gradient annulus of temperature of the two components, right? And that actually gives us a measurement of the heat flux through, to the sample. So we're measuring something related to the heat transfer, and in that way, if you actually run through the system of equations that are shown here, that in fact tells us in a direct way what the heat capacity of the material is. All right, and so that's kind of just a quick first order approach to it. But let me show you what that gets you to. Okay. All right, so instrumental components, right? And it gets a little bit more complicated, for example, in a power compensated DSC, although, and I have to admit, I don't know which is more common. Anytime I've ever done a measurement or have been involved with one, it's been on this class of instrument, and I don't know, if I've been lucky and this is the more expensive form, or I'm unlucky and this is the least expensive form. It is what it is. But if you actually look at this, what this is like an instrument that works in a very different way, and basically what it is, it's like two instruments. You have two ovens. You have one for the sample, one for the reference. You have control electronics to control each of these, and you have systems of temperature measurements for both that are independent. So very high accuracy power supplies, very well regulated oven designs, and these two things are then compared to one another, and the information basically extracted from the power requirements that are needed to drive one channel versus another in such a way as to maintain constant temperature at the two samples. Okay, so what is it that you would see by DSC? And we go back to the earlier example from the previous lecture. And basically, we see exactly the same sort of thing, but with a little bit of difference, right? So we see exo and endothermic processes, and they go one direction or another depending upon the convention by which you've set up your instrument. That all exothermic processes have to go in one direction, and exo in one direction, endo in the other, and of course we went through and described how this corresponded to the glass transition shown down here, the crystallization temperature, where the amorphic region is accreted into crystal, and the melting point. Okay, but now there's something else that happens from this, because we can actually look at the details of the line shape, and it turns out that this plot here shows a particular line. That line actually then is used to not only say something about and the integration of the peak areas, right? So the line is used to say something about the temperature at which a phase boundary is crossed. Like, for example, to undergo a net crystallization process, to undergo melting, but also via the integration, we can actually say something about thermodynamics, because of the fact that this information can be used to extract as we noted, the heat capacity of the material. And actually, what that's fundamentally saying is that we actually know what the net exothermicity or endothermicity is of the various processes. Now, here's an illustration of the wide diversity of samples that can be analyzed. So the top one is showing transitions to the melting point through several polymorphs of crystalline forms of carbon tetrachloride. I know, not so much of what many of us would consider to be a useful material. You may be perhaps a useful solvent, but not a structural material in any sense. But you can see these polymorphs are running from monoclinic, rhombohedral to cubic, and finally to the melting point. DSC can be used to monitor mixtures. Or here's a mixture of crystalline polymers, showing in fact the melting transitions of a complex mixture of polymers. I've never encountered a mixture that looks like this in the real world, but it does make for a nice example. Low density polyethylene, high density polyethylene. polypropylene, nylon 6, nylon 6,6. If we go back to the earlier lecture, I showed you examples of the vibrational spectroscopy of nylon 6 and nylon 6,6. And I said, if I asked you on the basis of spectroscopy alone, and just spectroscopy alone, tell me which is which. I dare say you would find that to be a very challenging assignment to do. But here you see a measurement, while not necessarily, unambiguously telling you that a sample was either nylon 6 or nylon 6,6. If in fact, you had vibrational spectroscopy that identified perhaps, one or the other, with some high certainty, a DSC measurement might actually then go ahead and do an affirmation that one or the other, or in fact a mixture of the two, were in fact present in an unknown sample. So you can see how this might start to become like a really useful form of measurement. Okay, so DSC is carried out with a linear temperature ramp. That being the most common way of programming data. And it provides information about melting points, glass transition temperatures, for semicrystalline and crystalline polymers. It's easily used to measure, for example, thermodynamic parameters associated with like processes that we saw in TGA measurements. So, for example, we have the loss of hydrating water molecules. We may want to know something about what the heats of hydration are, and we could actually measure those underlying thermodynamic properties by doing DSC measurements coupled with TGA measurements, one to tell you things related to mass and the other one to tell you things related to the underlying thermodynamics of the mass loss process. Okay, and as I had mentioned in an earlier lecture, the concerns about polymorphism in certain substances or materials is a thing that's particularly important, and in the pharmaceutical industry, it's like utterly crucial. And here's an example of DSC being used to assess the presence in qualities of polymorphic forms of a particular pharmacological agent. I'll tell you another place where it shows up is like, for example, in the area of explosives, which are, there's like some kinds of materials that are in fact, what people would call, sensitive compounds, and others that are insensitive, and sometimes you have to be careful doing thermal measurements on explosive materials. That's a whole other form of art, but and on very small sample sizes, I might add. Thermal measurements are frequently used to assess the states of materials, right? So that's not only just a quality control mechanism; it could actually be even an essential safety metric. For example, knowing that the particular form of a drug being administered actually corresponds to the therapeutically valid form of that drug. Okay. So, that's a really powerful example. And this actually shows, in point of fact, how we can actually use that measurement to deduce features of the underlying thermodynamics. So I showed these line traces being superimposed. And in point of fact, in the extended slide set, there are examples that lay this out. Typically what you do is that, you run a measurement, and the software is very good, and it tells you these outcomes as readouts. And I think most people just take it as a given, and that's like a nice thing because it makes it accessible, but it's also a little bit dangerous because it means you don't really know where it's coming from or what it's actually saying, or is the analysis valid. But in point of fact, these measures can be used to tell you something about the underlying thermodynamics. So these plots, right, are an example. So data analysis. Let's just kind of go through it in simple form, right? This is for a case of a high density sample of polyethylene, and by the convention laid out here, we see a number of transitions, right? Obviously some corresponding to glass crystallization and melt transitions, right? And melting point transitions, phase changes. Right, and so you can integrate the area on the curve as a function of time, and the signal is power, right? Watts to joules per second, right? And you can determine the average heat capacity and entropy of the process, right? And so and basically you have essentially all the information, all the thermodynamics, right? We know the heat capacity at constant pressure, right? We know delta H. We know in essence the entropy as well, right? So things to consider. So I would say work through the examples at the end of the extended slide set to make sure that this seems comfortable. If you have a broader interest in it, but you can see that clearly. This is the kind of information that in some contexts would be very valuable to have. Okay. I'm sorry for the quality of this slide. It did not come across very well. It's a little bit blurry. The point being laid out here is that, as before, with as noted with TG and DTA measurements, the temperature ramp rate matters, right? There is sort of like an underlying kinetic attribute associated with these measurements, and I think the easy way to understand, like why it would be sensitive, is to imagine, how this measurement would go in each of two limits of temperature scan rate, okay? And that is, in the first case, I scan temperature exactly at a rate of 0 degrees centigrade per second, okay? I mean, basically not at all, right? There's no data, okay? And then I scan the temperature at, 10 gajillion degrees centigrade per second. Basically, from room temperature to supernova in a femtosecond. And at that limit, there's no information either. It's like way too fast, right? So, there are in fact optimal scan rates, right? So like the data here shows the kinds of, offsets that you get in peak shape changes by, like, for example, temperature ramps done at 10 degrees centigrade per minute or 100 degrees centigrade per minute. And, so, typically scan rates are the order of, a number of degrees centigrade per minute. It's like kind of, quasi-equilibrium measurements, not, wickedly fast measurements, where you're, like, for example, ramping temperature by, like, say, 20 degrees centigrade per second. That would be, relatively, a fast temperature ramp profile. Okay. So, so heating rate. If you heat too fast, basically, you change line shapes, you drive transitions together, in such a way, by broadening, the temperature evolution profiles, and the data become hard to interpret as a result. The kinetics of decomposition, right? The sample size matters. You have to worry about mass transfer characteristics. So, like, the samples can't be too small because then, they're too small to measure. But if they're too big, you have to be careful, that in fact, the temperature ramp rate is not mitigating efficient heat flow, so that you're actually measuring a hysteretic property on the sample. And so, and as I said, anything that impacts heat transfer, would be, in fact, deleterious. So, for example, if we have multi-phase components which actually might, like, segregate during the course of analysis, or thwart reaching steady state in some way, that could complicate an analysis. All right. So crucibles that are used for this, and the point here being is that you have to do analyses in materials that are basically inert, and sometimes there is some requirement to actually use materials that can be pretty pricey. For example, platinum crucibles, if you have really reactive materials, and you have to go to extremely high temperatures, but like for example, ceramic crucibles, frequently can be used with many classes of material. Aluminum is definitely the most common materials used. Okay, combined techniques. And we noted this in the last lecture. There's lots of combinations. Mass spectrometry is really very valuable. And actually, it's becoming increasingly common to find these kind of couplings. So, for example, if you hook a residual gas analyzer, basically a quadrupole mass spec, directly to the gas evolution port of a TGA or a DSC, and as I said, a lot of times these are the same instrument now. You can then go ahead and mass analyze the evolved gas and determine what the compositions are for the materials that are being lost. And so in this way, I might go ahead and do a mass analysis of things that I'm seeing evolve during a TGA profile. And so, for example, that's illustrated here. Loss of retained solvent is being assessed by this analysis, right? So, and they, what they've done is they've showed, single mass profiles for mass to charge ratio of 31, mass to charge ratio of 43, and you notice how those masses are peaked at particular points of the thermogram. Right, and one of the other things you'll notice is that, right, for example, you see a secondary peak in the M/E 31 profile. Right, so right there, that actually corresponds to the place where the M/E 43 peak is, and that's actually kind of interesting. But that's like the nature of mass spectrometry, right? So here's a detail: these ions are not being directly desorbed into the gas phase, as would be the case for a SIMSA measurement, right, where the ion event generates an ion liberation event, right? These are being generated by the ionization of neutral molecules in the gas phase. They're ionized via what's called electron impact ionization. And so an electron beam is present at the front end of the mass analyzer, and that electron beam hits molecules that come into the ionizer region, and that electron molecule collision basically not only generates a positive ion by knocking out an electron, it deposits enough energy into the molecule to fragment it into pieces. So, an acetone molecule will break up into a number of pieces, and one of the pieces that acetone gives off is actually at the same mass as is one of the masses characteristic of the methanol molecule, right? So, in point of fact, you have to know a little bit about your mass spectrometry to know how to unambiguously interpret, things like this. So, that one is methanol, and that one is acetone, and it's actually possible then to say something about the quantity of material that was present and retained as an impurity in this sample based on this data. So clearly very powerful. Other kinds of analyses have been done as well. So, for example, this is a coupling that's done between a TGA and an FTIR, right? So, basically, the input could be coupled to a light pipe, which then allows you to do a sampling via kind of an internal reflection technique of compounds that are present in the gas phase, and then we can identify a component from its vibrational spectra. Okay, so. That brings us to the end of thermal analysis. Again, just the sort of note in closing. These are, in some sense, amongst the simplest measurements you can do, but in another, very clear regard, amongst the most important that frequently get done. Right? I know of nothing that we tend to do as a routine analytical measurement, right, that reports most sensitively on the behavior of how things, will be years from now, right? Will this compound, will this composition, will this structure be stable, 40 years from now, 10 years from now? What can I expect after, the first winter in the field in Sweden? We're exposed to snow and freezing temperatures and, and thaw, freeze cycles, etc. This is the kind of testing that you do to answer simple questions like that. Is my speciation pure? Do I have a pure phase material? Right. So if I want to know do I have a pure phase material, one of the things I can do is to, for example, heat it and look to see if there's some underlying phase change that happens. Like, do I change one polymorph to another, on and on. So I'll close here and thank you and look forward to seeing you at the next lecture.